Okay, I'm going to show you how to do this first paper right here, this applications, mostly because my voice is giving out, guys, so hopefully it doesn't give out throughout the video. But anyway, so we have this word problem that's talking about a combustion engine and a piston in the cylinder. A lot of physics stuff here, okay? I'm not going to read this to you, but basically this is our equation that's going to model this thing going up and down, being moved by the piston, okay? Where t is the time in seconds and d of t is the displacement, so as it's moving. The first question is asking, what is the amplitude of this sinusoidal function? So for amplitude, we're looking at the number in the front, so that's going to be 3.8, okay? So my a is equal to 3.8. And as far as how this is interpreted in the context of the problem, this is just the rate at which the piston is rising and falling. Okay, so it's rising at a rate of 3.8. Okay, next question is, what is the period of this sinusoidal function? So remember that the period is equal to 2 pi divided by the frequency. So we have to find out what our frequency is, which is, in this problem, the number in front of the x, or in this case, the t. So that would be this right here, 50 pi. So we're just going to go ahead and divide this. 2 pi divided by 50 pi. Okay, that reduces to, let's see, the pi's cross out, 2 over 50. If you plug it into the calculator, you're going to get 0.04. Okay, and this is represented as the seconds it takes for one cycle. In other words, for one cycle of this to turn right here. Okay, so if you're not too sure about this part, the interpretation, don't worry about it. I'm more focused on the math part, okay? Because personally, I'm not too savvy on this either, but we do know the math, okay? Next question, if the piston completes an up and down cycle at this rate, so at this rate right here, or over the period, how many revolutions would the crankshaft turn per minute? So they want per minute. We're going to go ahead and convert this. We have it in seconds, so we should know that one revolution happens in 0.04 seconds. Okay, we've done this before where we kind of make like a little chart. We want to do it in minutes, so I know that there's 60 seconds in 1 minute. Okay, and that's pretty much it. I want revolutions per minute, so I'm going to go ahead and multiply this out. So 1 times 60 divided by 0.04. You can use the calculator for that. I'll go ahead and do that real quick. So we're looking for a calculate page. So 60 divided by 0.04. Okay, that gives us 1500. So the answer for this is just 1500 RPM, revolutions per minute. So far not too bad, right? Okay. Next question, determine a good graphing window to view several cycles of this function. So this one I do want to kind of go over. Hopefully I don't mess it up because it's kind of weird when we're graphing trigonometric functions. So here's the calculator. Okay, we're going to go ahead and go to a graph. And we're going to go ahead and plug in this function right here. So that would be 3.8 sine. So sine is here where it says trig. Okay. 50 pi, so my pi button is down here somewhere, pi, there it is. And we're going to use x because we don't have a t-axis, we have an x-axis. So there we go, there's my function. Let's go ahead and press enter, and there we go. Okay, so they're asking us for a decent window of this. In this one I can kind of see the bottom and the top, which would give us our amplitude. So I'm going to say that between what I have right here, actually it works pretty nicely. So for my range, so my y values, okay, so y values, we can say between, I don't know how to spell between, okay, let's say -7 and +7, okay. For the x values, because this is a word problem, we can't exactly start at 0, okay? So I'm going to go ahead and just say from 0 on. So we can just do, well, quadrant 1 works. So how do I put that? Let's see. We'll say 0 and at least, excuse me, 1 cycle. So 10-ish. I don't know. I'm not too picky on this part. Okay. Last part, letter E. So this one says many engines run on 4 cylinders. This means that 4 pistons are attached to the crankshaft and must be engineered where they rise and fall even time intervals. So in other words, you're going to have 4 of these going on at the same time. And they want us to go ahead and kind of reconfigure this original function into 4 different types that we can use. So if you look here, we have those graphs, okay? And we're going to kind of see how did we change these graphs, okay? So Y1 is the original one. So that one, I'm going to do it in pink. That's what I have. That's this one right here. And that's our OG, so to speak. Okay, and we're going to compare it to the other ones. So let me get a different color real quick. So let's look at number 2. Here's number 2. Notice that from here to here, it just kind of shifted over. Okay, we're going to go ahead and assume this is in pi half intervals. So in other words, this is 0, this is pi halves, pi, 3 pi halves, 2 pi, and so forth. So from here to here, it went pi halves to the right, and pi halves to the right is just minus pi halves. So for Y2, we're going to say it had a phase shift pi halves right, which means the equation would look real similar. So 3.8 sine, and then a 50 pi. Okay, and we're just going to go ahead and do t minus pi halves. So we do have to rewrite it in terms of how the vertex form for this is. So back in our notes, we had our frequency here, and then our x, and then the phase shift over here. Okay, so there's the first one. Well, the third one, let me grab a different color for that one. We have that it's, let me see, it's right here. Okay, so compared to my original graph, let me see. So here's the pink one. It kind of looks like it just flipped over. Do you see that? So if you follow the green one that I'm highlighting right now, or outlining, compare it to the pink one, and they're just exact reverses of each other, like they flipped each other. So this is a reflection, okay, over the x-axis, which means that this is going to be negative 3.8 and all of that. So sine 50 pi t. And that's it, okay? And for the last one, let me grab one more color. Let's see, I have turquoise. Okay, so for the last one we have, this is our fourth one. Here it is. And it is, it looks like it kind of just moved back. Yeah, so it went from here and it moved back by pi halves. So that would be plus pi halves. Remember, going backwards is the opposite. So to the left would be, so this one right here is going left by pi halves, which is a phase shift. Okay, so this is a phase shift by pi halves. So that means my equation is going to be 3.8 sine 50 pi, just like the first one, but we're going to do plus pi halves because remember that it's always opposite for that. And that's it. So go ahead and do this one, complete it, and I'll let you know what to do after that in class.